Installing mental model for hash maps. You have a million contacts in your phone. You type a name and it appears instantly, not after scanning 1,000 entries, not after checking 100. Instantly. How? A hash map takes your key, say the name Alice, and feeds it into a hash function. This function scrambles the input and produces a large number. That number gets reduced, usually by dividing by the array's size and taking the remainder, into an index. The key insight is this: you don't search for where Alice lives. You calculate it. One operation, direct access. No scanning, no sorting, no comparisons. Just math pointing you to the exact slot. This is what makes hash maps feel like magic. Any key goes in, a precise location comes out. Store a value there, and later, the same key leads you right back. Every time. It's constant time lookup. O of 1. But here's the problem. Hash functions map an infinite number of possible keys into a finite number of slots, which means eventually, 2 different keys will land in the same bucket. This isn't rare. As the table fills, collisions become unavoidable. So how do we handle them? The classic approach is called chaining. Each bucket holds a linked list. When 2 keys collide, the second one just attaches to the chain. To look something up, you hash to the right bucket, then walk the list. Simple, but there's a cost. Every pointer you chase is a cache miss because those list nodes are scattered across memory. The alternative is open addressing. Instead of a list, you look for the next empty slot in the array itself. Linear probing checks the next slot, then the next, forming clusters of occupied entries. There's an elegant variant called Robin Hood hashing. When a new key collides, it checks. Did I travel farther than the key sitting here? If so, it swaps in, and the displaced key continues the search. It's stealing from the rich, keys with short probe distances, and giving to the poor. The result is every key ends up roughly the same distance from home. As entries pile up, the hash map fills. The ratio of entries to buckets is called the load factor, and every implementation draws a line, a threshold where performance degrades too much. Java draws it at 0.75, Python at 2/3, Go at about 0.8. When you cross that line, something dramatic happens. The table doubles. In most implementations, every entry gets rehashed and placed into a new, larger array. All of them redistributed. It sounds expensive. Doubling a table with 1 million entries means 1 million rehash operations. And it is expensive in that one moment. But here's the elegant part. Think of it like a savings account. Every time you insert an element, you secretly set aside extra coins. 1 coin covers the insertion itself. 2 more are saved for later. When the table finally needs to double, every existing element already has enough coins saved up to pay for its own rehash. The bill was prepaid, 1 insert at a time. This is why computer scientists say hash map insertion is O of 1, amortized. Any single insert is cheap, and the rare expensive resizes are already budgeted for. The average cost per operation stays constant, no matter how large the table grows, and that's what makes hash maps scale. Not just the hashing trick, the fact that growth itself is built into the cost model. Real hash maps carry battle scars you won't find in textbooks. Take Java. Once the table is large enough, when a bucket's chain grows to 8 nodes, the hash map quietly converts that linked list into a balanced red-black tree. Lookups go from O of n to O of log n. Under normal conditions, this almost never triggers. The probability is vanishingly small. It's armor against worst-case scenarios, and the worst case is real. In 2011, researchers demonstrated that a single HTTP request, just 100 kilobytes, could freeze a web server for 90 seconds. The attack was simple: craft parameter names that all hash to the same bucket. Suddenly, O of 1 becomes O of n. Repeat that across every lookup, and the server is pinned. This is called hash DOS, and it affected virtually every major language: Java, Python, Ruby, PHP, JavaScript. The defenses are now built into the languages you use every day. Python switched to siphash, a keyed hash function with a random secret generated at startup. Same string, different hash every time you launch Python. Go randomizes its hash seeds too. And Java added treeification as a safety net. These protections run silently. every time you use a dictionary or a map. Most developers never know they're there, but now you do. Cognitive architecture updated.